Friction deserves a blank slate. Here we go. Friction. The first kind is static friction. Static friction is what you have when an object is not moving relative to a surface. So say you have that's a flat surface, believe it or not, with an object resting on it and you're pushing on it. You apply a force to it. Well, as long as it's not actually moving, right, not yet beginning to slide, you have static friction opposing motion. All right, so static friction is actually only going to be as big as it needs to be in order to oppose motion. So we can say static friction is going to be less than or equal to, here's your first formula for friction, mu times the normal force. Or if you prefer, you can say friction is fun. Get it? Because it's F-U-N. Physics jokes. Okay, so friction is fun. We will actually say that like all the time. This one, though, because it's got that less than or equal to sign, though, is going to be specifically for static friction. Okay, so static friction is, it can change in magnitude depending upon how big it needs to be. If I didn't push on this object at all, there would be no static friction opposing its attempted motion. All right, kinetic friction is sometimes called sliding friction. That one's real simple. It's just equals mu times the normal force. Actually, these two mu's are different, though. There's a different coefficient of friction for each of those two types of friction. If you're wondering what I mean by the coefficient of friction, that's this thing here, the letter mu, or I usually say mu, but apparently it's mu. And of course, the normal force is whatever the normal force is. So the friction force depends upon the normal force and this coefficient thingy. All right, that coefficient thingy is going to depend upon what the surfaces are. So if you have, say, sandpaper against wood, that's going to tend to dig in and you'd have a pretty large coefficient of friction. Rubber against like just about anything is going to have a large coefficient of friction. On the other hand, if you're talking about ice on Teflon, then mu is going to be very small. But it does depend upon both surfaces. All right, last kind of friction is not going to work like either of these two, and we'll basically never talk about it, and that's fluid friction. Next year, if you're in AP, we will talk about fluid friction. That's things like air resistance. And they're really frickin' complicated, which is why we're not going to talk about them. If you want to know why they're complicated, it's because they are proportional to velocity, which gets messy. You have to do calculus for it. So we will not discuss them as best we can this entire year. Okay, so really, these are the two that you got to know about. Now that we've said a bit about the different types of forces, let's get a little more formal. We have Newton's laws of motion, which you read about in the book. And if you recall, there were 3 of them, Newton's 3 laws of motion. So we had the first law was basically something in motion tends to keep on moving. Or, said another way, an object tends to maintain its state of motion or rest unless acted upon by an outside force. Okay. Now, that actually is a pretty fundamental statement. If you go back to, I don't know, prior to the 1600s, prior to Galileo and Newton, and those guys are pretty foundational in what we understand about physics, or at least classical physics. People had this idea that the natural state of things was to stop moving, which makes a certain amount of sense because you have never seen a perpetual motion device. That's because they don't exist. Things don't keep moving forever. That's not your normal experience, right? Even if you're, like sliding something across, a smooth pond, right? An ice skater on skates can, go around the rink for quite some time because there's very little friction, but they will eventually stop because there is some amount of friction. Okay, and so without that understanding, though, that they are being acted upon by a force, which is to say friction in most of these cases that you can think of everything stopping, without that understanding that there's a force acting on them, it would be natural to think, well, things just stop moving. Okay, and so that's kind of where everybody was prior to Galileo and Newton throwing around those ideas. Okay, so it's actually pretty foundational, which actually brings up something that people get confused about all the time, even now, right? Don't be like, oh yeah, those silly people back in the olden days. It happens all the time where I will ask people to write an equation for, let's say, the sum of the forces on an object which is just sliding along. There it goes with a velocity, right? There it is, sliding along on a frictionless surface. And I'll say, write an equation for the sum of the forces on this thing, and people will want to put that velocity in the force equation. What makes it keep moving, Mr. Errico? There has to be a force acting on it. At some point in the history of that object, a force did act on it. That is why it is moving. However, it's the wrong question to say what makes it keep moving. It's more appropriate to say what makes it stop moving, right? That's really the question, okay? So if nothing acts on it to make it stop moving, then it keeps moving. Okay, so a velocity does not belong in a force equation because there's no force required to make it keep moving. Rather, it's just the opposite. A force must act on it to make it stop moving. All right, let's do the second law. There it is. One of the simplest equations you'll ever see. F equals ma. And yet, it has such profound consequences. Okay, so this is one of Newton's two laws, or three, one of Newton's three laws, excuse me. F equals ma. And what it says, the way Newton phrased it, is more or less to say that mass and acceleration are inversely proportional. Let us have a simple demonstration of this fact. Here we have two objects. Well, there's a bunch of objects in the picture, but the ones that we're going to consider are this small child's toy, which has wheels, and this piano, which also has wheels. As you can see, oh, look at that. Poking the child's toy on wheels produces an acceleration. Poking the... No, not so much, right? Okay, now, it's, I think, pretty simple for most people to explain what's going on there. On the other hand, it's actually more complex than it looks like. But let's just deal with the simple ideas first, okay? Clearly, the toy had a smaller mass, so we were able to get a larger acceleration out of it. Okay, so the mass and acceleration are inversely proportional. Now, in fact, there's another reason why the piano did not move. If there were no other forces acting on it besides my finger, the piano would have, in fact, started to move in the direction that I poked it. Okay, that's a consequence of saying F equals ma, right? On the other hand, the piano must have been in equilibrium. So take a moment and think, what other force prevents the piano from moving? Yes, friction. That's right. So even though it's on wheels, right, wheels are not perfect, there's some amount of friction in the wheels, and that friction is what prevents the piano from moving. Okay, so absent that friction, the piano actually must move. If you're not good with this, let's take the piano to space for a moment. Usually I put elephants in space, but we could take the piano to space this time. If you've got me and the piano in space, and I push on the piano has to move. There's nothing holding it down. There's nothing preventing it from moving in a particular direction. And so if I push on it, it is going to move. All right, we'll actually bring up the piano and the astronaut in space again in a moment. Well, hey, actually right now, because we're going to do Newton's third law. So his third law states that if I push on the piano, in fact, the piano pushes back on me. So this statement, for every action, there's an equal and opposite reaction. That's what it's talking about. The way we phrase that in physics is to say that it's an action-reaction pair. If I push on the piano in a in a very real sense, is actually pushing back on me. If you don't believe that, picture that for a moment, right? Me and the piano in space. If I push on the piano does have to move, but actually mostly what's going to happen is I'm going to go flying backwards pretty fast, and the piano is going to go flying in the other direction not quite as fast. If you need further proof that the piano pushes on me, which sometimes people need more proof on this, let's just for a moment push on the desk while you're sitting in your stool. If you push really hard, what will happen to you? If you thought to yourself, I will tip over, that's true. You will tip over because, well, actually not because you pushed on the desk. Let's think about that, right? You are pushing towards the front of the classroom, but you are about to fall towards the back of the classroom. You did not push yourself over. Let that sink in for a minute. No, you didn't push you over. The desk pushed you over. Granted, it was because you pushed on the desk, right? Okay, so that fine, that should make sense to you, but the reason that you actually tipped over is not because you pushed on the desk, it's because the desk pushed back on you. Okay, if that desk were on like really great wheels, instead of it pushing you over, it might just slide the other way, okay? Fine. So that's the idea of the action-reaction pair. This is going to come up like all the time, where you're going to have to decide, all right, what's the magnitude of these two forces acting on something? And if they are an action-reaction pair, they actually always have to be equal. If I punch the board, I will hurt my hand. And the reason I will hurt my hand is because however hard I hit the board hits me. This is true based on the action-reaction pair. Now, a more simple consequence of that is this. If you have, here's a surface and an object resting on it, right? Gravity pulls it down this hard. There is going to be really a normal force, though, between the two surfaces, right? Where the surface of this object is pushing down on the surface of like the table, and the table pushes up on the object, right? The normal force and the gravitational force, the weight, aren't actually an action-reaction pair. They don't have to be equal in magnitude, right? If I come along and I push on this, there, I'm applying a force downwards, right? The weight doesn't go up, but the normal force does, because it has to be larger now to resist the extra force pushing downwards on it. All right, so that's Newton's three laws. They're going to be applied like all over the place. Let's go ahead and flip to the next page in the packet. And now might actually be a good time for me to break to part 3 of this extremely thrilling simulating video. So here we go.